Hey everyone, actually no, specifically, hey BC, this is for BC only. If you're an AB, please click away. There's no point in you watching this. Come back next year. So, and just a reminder, if you hear loud noises in the background, it's you, so just blame you. So I'm gonna go through and do the homework, and probably make some mistakes along the way. Feel free to call me out for it. But yeah, here we go. So we're doing integration by parts. Oh, and it says not all require integration by parts. That is a good clue to us. So remember when we're doing integration by parts, so like I look at this first one, x sine x. If I'm kind of going through the flow chart of like things that I want to do, it's like, can I do an easy one? If I know like an easy trick, I should do that. If I don't, then I'm going to look and see, is it one of my secondary methods like integration by parts or U substitution? So integration by parts, we want to say, hey, is there something that I know the derivative of, and is there something that I know the integral of, like separately? And I like the way that Nick put it in class. It's kind of like reverse product rule. So when we have two things multiplied together, a lot of times that is integration by parts. So especially when we can't see a simple like popping out from U substitution. So again, this one I have x sine x, and I know, I'm going to say I know the derivative of x, and so I'm going to pick that for U, and so my du then is going to be 1 dx, and I know my, then if I say v, well hey, v we can say is sine of x. Oh no, I don't know v. I know dv, right? We know a u and we know our dv. You can say dv is sine x dx, and then the integral of that is, and I want to say it's cosine, but I need to think about the sine of it, because to take the derivative of cosine, I get negative sine. So I need to slap a negative on cosine then to make it work. So now if I go in and I apply our integration by parts, which is uv minus the integral of vdu, well, I know u, okay, so it's just putting things where they belong, right? U is x, v is negative cosine x. I'm not going to write u times negative cosine x. I'm going to put the negative out front. So there's our uv, then minus our integral. Oh, and v's a negative, right? So we'll put a plus there. And then du was just 1 dx. And now we've got a really simple integral right here to solve. We've got our negative x cosine x, and we know the reverse derivative of cosine is just, is it regular sine? Because then the derivative of sine is cosine. Yep. And there we go. And I'm pausing to wait for you to yell at the screen, because there is a plus c. So if I was going to edit my videos, I would definitely have a plus c counter, like missed plus c's down in the bottom left or something like that, because that would be fun. But you know, editing takes hours and hours and hours, and this doesn't, because I'm lazy. No, I'm efficient. Let's call it that. Okay, so in number 2, it feels pretty similar. I think if I said u is equal to x, my du is equal to 1 dx, then I can just say my dv is equal to cosine of 5x dx. Oh, but I can't just say v is sine 5x, right? Because the derivative of that pops a 5 out front. So I'm going to have to divide this by 5. So I'm going to say 1/5 sine 5x. And we very well could do a u substitution problem to do that, like officially. But I hope that this idea makes sense. Like when I take this derivative, having the 1/5 there is really the only way to have the 5 cancel when it pops out. So we're like reverse canceling almost. So then when I apply the formula and I get x times 1/5 sine 5x, you could write x over 5, you could write 1/5 x, however, whatever you want to do. minus, and there's no negatives this time. Ugh, 1/5 again. So I'm gonna write 1/5 integral. Remember, that's a constant. We're allowed to pull it out. So I gotta write v there, sine 5x, and then du is dx. So, oh, and again, this integral here is not super hard. We know the antiderivative of sine is cosine, but we need a negative to cancel the negative. So, and remember that a 5 is also going to pop out when we take this derivative, so I need a 1/5 to cancel the 5. So, and this all comes down. So, got some double negatives there, and I got a 5th and a 5th. So I can say, I could, you know, do some factoring if I wanted to, like pull a 1/5 out of everything, but plus so yeah, I think that handles it. And remember, a great way to check yourself with these is if you were to take this derivative, you'll wind up with what we started with, theoretically. And just remember, like with this one, we're going to have to do the product rule, because it's x times sine of 5x. The 1/5 isn't important, but the x is. And I did that on purpose. I did actually. I was like, you know what? I'm going to wait to put the plus c in for a little bit. Because as Michael Caine said in some of the, in I forget which Batman movie, I think it's the one with the Joker, you know, he goes, some people just want to watch the world burn, you know, like, ha. Alright, so let me pause real quick. Alright, so I'll say my u is equal to x, du is equal to 1 dx, and then we'll say that we don't know v yet, but we know dv is equal to e to the 8x dx. So then v is equal to the integral of this, which is just going to be e to the 8x. But remember, when we take this derivative, it's supposed to turn into that. An 8 pops out, so I need to have an 8th out front. So when I try this, so uv, so x and that, x over 8 e to the 8x minus v du. I'm going to pull the 1/8 out front, e to the 8x, du is just dx. These are great. I love these. I want to be on the first like 5 questions for the rest of the day. I never want to have to move on past them, because these are just like, can I just have these problems? Can this just be the test? So in this one, a 1/8 is going to pop out again, so it's going to be 1 over 64 e to the 8x. Oh no, Sophia's like working right along at the same pace as me, so now I'm spoiling all the thinking for her. Oh, I'm ruining this. Alright. I am actually going to... Oh no, 4 switches it up. Sweet. Oh no, 4 doesn't switch it up enough. I'm going to jump on a little bit later into this. I'll be back. Alright, so I've got my coffee, and let's keep going. Alright, so in this one, in number 4, it looks messier at first, but just remember that the derivative of 6x plus 2 is still pretty simple. So I'm going to say u, I'm going to set equal to 6x plus 2. Is that too small? I think that's legible. Then du is equal to 6 dx. And then I'm going to need to find v and dv. So dv I'm going to say is e to the negative 3x dx. So then my v is going to be the same thing, right? E to the negative 3x. But we need to account for, when I take this derivative, what's going to happen. So a negative 3 pops out, so I'm going to have to divide this by a negative 3. So I say negative 1/3 out front of that. So I think this should just be a simple application now. So UV, so negative 1/3 times 6x plus 2 times e to the minus 3x. And notice how, like, you can write this in any order. It's being multiplied. It's just, you want to pick an order that's convenient or simple to write. And I generally prefer to put like e to the x's and ln x's, sine x's. I like to put them at the end of like any polynomials because it makes things look a little clearer. So I just, took this 6x plus 2 and the negative 1/3 e to the negative 3x. I took those and, broke it up into easier to write things. So now we're going to take our du and our v, and remember that constants are allowed to get pulled out front. So, and it's, so 6 1/3. It's going to be negative 1/3 times 6 out front, which is 6/3, which is 2, so negative 2. So remember that in the formula it's minus, so minus a negative 2, so I can actually write plus. I think so many mistakes on these happen just from little sign mistakes and stuff. And then v du, so e to the negative 3x du, and we already took care of the 6. So I would recommend trying to write as few steps of this monstrosity as possible. I know some people in class, they'll write 10 lines for it, and you totally can. And I don't want to stop you from doing that, especially if you make mistakes when you skip it. On the AP test, they're not going to be 45 problems like this. This is going to be 1 or 2 of the 45 multiple choice problems. Or it'd be like a part A of a free response question. This isn't the type of question they throw at you as like the big stuff. Okay, so now we've got the plus 2, and we'll take the integral of e to the negative 3x, and we'll have the plus c on the end. So that's just e to the negative 3x, and a negative 3 pops out when we take the derivative. So that means a negative 1/3 unpops out to make the 3 cancel it. So my final answer, I got negative 1/3 6x plus 2 e to the negative 3x minus 2/3 e to the negative 3x plus c. There we go. So, all right, how am I doing on space? I think I want to move up a little bit. All right. I feel like this could be brighter. All right, let's see if this is any better. So, let's see, are my fingernails clean? Okay, so, it's probably not going to be any worse. So, okay, here we go. So our next one, okay. So we can say our u is equal to x, and we can say our dv is equal to cosecant squared x. Okay, so we should talk about why we know to pick those. When we're doing integration by parts, we want to say, okay, which one's the easy one to take the derivative of? Or which one disappears when we take the derivative? So, like in number 3, e to the 8x is a pretty easy derivative, but the derivative of x goes away. And so that we always are hoping that we can use parts to make the next stage simpler. Or another thing to think about is cosecant squared. That is essentially the derivative of something else that we already know. So if you don't know what that is, I would go check your like derivative rules, but you really want to, as much as you can, as soon as you can, wean yourself off of always going and looking it up. And a good way to do that is to say, okay, I've now come across cosecant squared. I think that I took the derivative of blank to get it, and ask yourself what that is, and then go check. And if you were right, next time you encounter a cosecant squared, do it again. But you want to self-check first. That way we can self-correct, and eventually we'll get to a point where we don't need to check anymore. But it just takes some time. Oh no, I'm in the wrong orientation. I'm glad I didn't do any work. Okay. Oh, I hope this video still works.
You can edit out the centers, but it's the centers.
Yeah, but you have to have real software to do that.
I have a copy of the full like Adobe Suite.
All right, here we go. Wait.
At home.
All right, so we took the derivative of cotangent to get cosecant squared, but the derivative of cotangent turns negative, so I need to throw a negative out to cancel that. Oh, and I forgot to write the dx down here with the dv. Okay, so as we continue, we got our uv, so that's negative x cotangent x, and then minus the integral of v to u, and v is negative, so we're going to change that to a plus, cotangent x dx. So now I just need to find the integral of cotangent, and we did the integral of tangent in class, and so this is another one. I would not recommend memorizing this. Instead, I would remind you that this is achievable through u substitution. So I'm going to do this on a secondary piece of paper, so that then I can move it off to the side, because I'm just afraid it's going to take me more space. So, and I'm going to use a different color too, just to, because I can. So cotangent's cosine over sine dx, and my hope is for this to look like 1 over u du, or something close to it. And so what I'm going to do is I'm going to say, well, u, we'll say equal to the bottom, we'll call that sine of x, and then du is equal to cosine x dx. Oh my gosh, this is great, because it's literally just the u is sine, so down here instead of writing sine I can write u, and the cosine x dx that's effectively on the top is right there. I'm going to just write du in its place, so I can write this as 1 over u du. I figured there would be some kind of negative or something that pops out, but in this one there isn't. And then our integral of that is just the natural log of the absolute value of u plus c. So in this case, that's going to be the natural log of the absolute value of sine x plus c. So my final, wow, I've already done this one. That was so much less than I thought it was going to be. So we've got x cotangent x, forgot the negative, and then plus the natural log, the absolute value sine x plus c. And again, if we take the derivative, we get our answer, or we get our original problem. That's how we know that we're right. So, and the best part about this is, if you need to go back and look at something, you can always rewind and pause the video and all those fun things. So I will leave this here for now. 6. All right, worked with a few of you on 6, so I know 6 is a little messy. So I'll be right back. All right, so in number 6, we know that u is, well, I say we know. You know what, if I made u the square root of x, I'm able to take its derivative. The integral of ln x, I don't know if you remember, that was actually an exercise we did earlier. That was an integration by parts problem on its own, so I probably don't want to do that. All right, so been a bunch of interruptions today. Sorry about that. So again, I don't, taking the derivative, or the integral of ln x was its own problem that we did integration by parts. So I'm going to say u should be ln x, then du is 1 over x dx. Makes it nice and easy. And then we can say that dv is square root of x. And remember, square root of x is x to the 1/2 power. So then when we take its integral, we'll get x to the 3/2, because we add 1 to the 1/2. And then we'll bring the we're gonna like divide by 2/3, which for us the shortcut was you multiply by the reciprocal. Did I just say divide by 2/3? Sorry, we divide by this 3/2, which turns into a 2/3 when we multiply it out front. So doing all that, we wind up getting, so 2/3 x to the 3/2 ln x minus v du. So I can bring the 2/3 out front. There's no negatives to cancel the minus. And I have a x to the 3/2 times a 1 over x dx. So I'm going to mush those together and get x to the 3/2 over x to the 1. So I'm doing that because I can subtract, wow, I'm boring myself to sleep here. I can subtract the 3/2 and the 1 and get 3/2 minus 1. So 3/2 minus 2/2, 1/2. So this is just saying minus 2/3 integral x to the 1/2 dx. So I'm just asking for the integral of the square root of x, which we actually did a couple minutes ago. So that's 2/3, and I'm going to get 2/3 x to the 3/2. Bring down the stuff from earlier. This whole like leaving these things out, it's bad form, but like it's totally fine. No one's going to knock you for that. Well, I'm not going to knock you for that. Like you're doing like side work here. Plus c. So that's 4/9 right here. That's the only simplification that you could do. You could factor a 2/3 x to the 3/2 out of both of these if you want. That's fine too. I'm not going to do any of that, but you can do all that. All right. 7 x e to the x squared. Okay, here's the problem. E to the x squared does not have a standard integral. We do not know the integral of this. So because of that, I'm going to say that u is equal to e to the x squared. So then du is equal to e to the x squared again, but we got to multiply by the derivative of its exponent, which is 2x. And then we need to find v, but we know dv is equal to x, so that's x to the 1, so this will be x squared over 2. Or you can say 1/2 x squared, either way. So now when I plug in the formula, I'm going to get x squared e to the x squared over 2. And you can say 1/2 times that. I am just trying to switch up my formatting to kind of suit different people's writing styles. It's all stylistic. It's not correct or incorrect. Then we'll subtract the integral of v du. Uh-oh. So that's going to be, So v, instead of x over 2, I'm going to put the 1/2 out front. Du, or I can put the 2 out front as well. This is why it's better to kind of think about this before you write it all. And then times x e to the x squared. Hey, that's not helpful. This looks worse than my original. I've got x squared e to the x squared over 2 minus, that turns into 1, x cubed e to the x squared. Is this really worse? So I've been getting distracted and I've paused the video a whole bunch. So I'm just going to double check my work here. If u is that, then du is that. If v is that, oh, I feel silly, right? So this is all true, but instead of doing all that, I can say u is equal to x squared, and du is equal to 2x. And if I use that to do some replacements, then I'm going to have e to the u, which is now an integral that I know. Ooh, there's a dx here. And I have an x and a dx left. So I know some of you prefer to solve for dx, so I'm going to solve this for dx. So I've got x e to the u dx. And if I go and do some more replacement, x e to the u times du over 2x. Now the x's cancel. That's 1 over 2. So I can say 1/2 e to the u du. Integral of that is just e to the u with the 1/2 still out front plus c. Drop in my x squared. I feel silly. And I'm not gonna lie, I don't know if I would have gotten there. What reminded me of this is that Alexandra actually said, "Oh my goodness, I didn't have to do parts. That was just a simple u substitution." She said that during class today. That's honestly the only reason that I remembered that I'm able to do this. So, important lesson for us to remember here is that just because we're focused on integration by parts doesn't mean that that's necessary for every question. So I'm gonna have to stop for now, but hopefully I'll have more time later to come back, and I'm gonna do as much of this as I can, and then I'm gonna upload whatever I have on YouTube before I leave for the week. So, bye.